production. So what is pair production? Pair production is the creation of a particle and its antiparticle from a neutral boson. So what is a boson? A boson is a spin zero particle. And a photon is in fact also called a boson. Okay. More often than not, it is a photon of sufficient energy that materializes into an electron and positron. So an incoming photon materializing into an electron and a positron pair. Now this is a very interesting process. Then why doesn't all light basically become electron-positron pairs, if that was going to be true? There is a big reason for it. The big reason is that this interaction must occur in the presence of a particular kind of nucleus, or this will not happen. And that interaction, in order to conserve energy and momentum, must happen in the presence of this nucleus. Otherwise, why doesn't all light become electron-positron pairs? Why do we even exist? If that was that many electron-positron pairs just floating around, we will all be dead. So now let's talk about why this is. So that is called a pair production. And we can say for pair production to occur, the energy of the incoming photon must be above the threshold of at rest total mass energy of the two particles. So what is the rest mass energy of an electron? Anyone remember in MeV? Very good. 0.511 MeV. Wonderful. So the rest mass energy of one electron is 0.511 MeV. And the rest mass energy of a positron, which is the anti-electron, is also 0.511 MeV. So what is the total energy of the incoming photon? So the total minimum energy of incoming photon must be 1.02 MeV, at least. If the incoming photon has additional energy, that energy will be converted into the kinetic energy of the outgoing electrons and positrons. And in general, we know that the photon energy of 1.02 MeV correspond to about 1.2 picometer wavelength, which is the wavelength for X-rays. So in the spectrum, 1.2 picometers correspond to about X-ray range. And in nature, they are found as cosmic rays and emissions from radioactive nuclei. So then the next question you should be asking me, but when we go in for our X-rays, why aren't there electron-positron pairs being formed there? And the reason why that happens is because the X-ray range that we use for creating the X-rays that the human body is bombarded with is too low. Usually that range in the X-ray, in X-ray imaging, our machines are usually rated for 150 keV, which, right, notice it's 150 keV, whereas what is needed? 10 times more.
Yeah.
So that's why when we are bombarded with those X-rays, our electrons are not becoming.
It's gonna disappear.
Yes. You don't get skinny when you're going for an X-ray. Good? So the production of electron-positron pair from incoming light is called pair production. Now I said one other thing, then why are not more electron-positron pairs just being created everywhere? There's light everywhere, right? We are being bombarded somehow by cosmic rays all the time, and why is there not more electron-positron pairs? And there is one very important principle in play here, and that principle is called conservation. So in all of these scenarios, you have to have conservation. Conservation of energy and conservation of momentum. So when this happens, what different kinds of conservation principles are in play? Well, the first one is the conservation of electrical charge. What's the charge of a photon? Zero. So charge of photon must equal charges of electron and positron. Agreed? So the charge of a photon is 0. What is the charge of an electron? -1. What is the charge of a positron? +1. -1 plus 1 is? Good. So charges are conserved. Number 2, conservation of energy. Energy of a photon must equal energy of the electron plus energy of the positron. So first of all, minimum energy must be 1.0211 MeV, which means this should be 0.551 MeV plus 0.511 MeV. Number 2, extra energy, suppose it has, let's say it is 2 MeV coming in, the extra will be converted into 0.511 MeV plus 0.511 MeV plus the kinetic energy. Get it? It will be shared equally between the two. Carried away. Number 3, conservation of momentum. Now, momentum will not be conserved in isolation. In order to conserve the momentum, we will have to have a nucleus there that carries the extra momentum away with it. Okay? So in order to conserve linear momentum, we must seek help of a nucleus which will carry away enough photon momentum for the process to occur. Nucleus has a huge mass when we compare it to the mass of a photon. Does anyone remember the formula for momentum? mv, right? So if something has a huge mass but a tiny velocity versus something has a very tiny mass and has a huge velocity, right? Their momentums will be equal. One of those two things. So photon mass is very, because it only has mass when it's moving, right? As soon as it stops moving, it doesn't have any rest mass. Whereas a nucleus is huge as compared to a photon. But all of the photon's momentum will be carried away by the nucleus, right, in terms of becoming its mass. So you can say, because of the huge mass of the nucleus, it will absorb only a fraction of the photon energy, just enough so that the linear momentum is conserved in this scenario.